In Chapter 2, we're going to be going through how we can describe qualitative data. So between Chapter 2 and Chapter 3, we should be able to figure out different ways, graphically and numerically, to describe qualitative and quantitative data. We'll start off with qualitative just because it's more visual and so that we get that coding background to create graphs. So what we're going to go through today is go through different ways of presenting graphs for qualitative data by leveraging our knowledge of Python and programming. We will be going through different types of categorical data, as well as understanding what frequency, relative frequency, and percentage mean, because the first step is always to create a statistical table so that we can present our data. Afterwards, we'll go through pie charts and bar charts, which are very common ways of presenting categorical data. At the very last part of this lecture, I will be going through an object-oriented approach to creating figures, just so that, especially as a scientist, we can understand step by step what efforts are being taken to create your figure. Okay, so we're going to start with an overview of qualitative data. So first, we're going to go through what types of categorical data there are. Qualitative data is commonly known as categorical data because with qualitative data, we don't really have numbers to represent those types of variables. We have to filter our data through into different groups of categories. Once you have those categories, you can further narrow down what kind of data you have. You can have Boolean data, which is only just two values. For example, true and false, yes and no. That would be an example of Boolean data. And all of your data that you collect would have to be filtered and placed into one of the two categories. If you have more than two categories, for example, the one below where I have academic levels, you have undergraduate, graduate, postgraduate, and professional. That would be considered nominal data because more than two categories are required in order for you to represent your sample. Then you have ordinal data. So ordinal and nominal data both can be used interchangeably depending on whether you have order to your data or order to your categories. So for nominal data, if you have more than two categories, for example, you can take a look at the table below. If you have more than two categories and you can order them in some sort of logical sequence, then you can consider it ordinal data as well. So another example of ordinal data, apart from the undergraduate and academic level one that I have here, you can also have rankings and ratings for a movie, let's say, where you have poor, satisfactory, and excellent. These are three different types of categories, but there is a logical order to them from bad to good. So that would also be considered ordinal data. Next, I want to say that a lot of categorical data usually is presented at first with a statistical table, and usually a statistical table is enough for a publication or even for presentation of your qualitative data. But sometimes we want to display it in more fancy ways, so that's why we have to move on to being able to describe them visually through graphs. But before we even get to the graphs, we need to understand what metrics we use to describe qualitative data. And so there are three metrics. There's frequency, relative frequency, and percentage. So all three types of metrics are going to measure how often your category shows up. So these metrics give us insight into which categories are the most popular and which ones are the least popular. Just going to go on to the next slide. We're now going to go through frequency, relative frequency, and percentage. So with frequency, very simple, it just represents the number of measurements in each category from a total of n measurements. This usually comes from the data collection method. So you would just collect your data and you'd have your number of values for within that category. Most importantly, we'll want to work with relative frequency or percentage. Relative frequency is really just the proportion of measurements within each category. So if you have 20 measurements in one category, but you took 200 measurements, then the frequency would be 20 and the total would be n equals 200, and your relative frequency would be 20 divided by 200. So that equation is useful for calculating relative frequency. Now, in terms of Python code, we do want to try and leverage our knowledge of Python for this course. So it is okay if you use Python to get all of your values. There are two examples I want to go through, from first principles and then from a quick perspective where you can just use something that's readily available. So from first principles, let's assume X is a list of frequency values. So you have a bunch of data collected, and you already have a list of how many times your data shows up within a category. So we can define a function called relative frequency. Here, what it does is it calculates the frequencies of each of those values. You have the value, you count the number of values that take place within a category divided by the length or the total number of your values for each value in a set where you have a set of categories to look at. So this would be coding your relative frequency equation from first principles. However, it's just faster to use readily available functions. There is an available function from the pandas module. So you can use frequency is equal to pandas or pd.dataframe, where you're loading in some data into, I'll just say for short, it's like an Excel spreadsheet. You're loading something into a data frame. So you first set out your data. Let's say we have apples, bananas, oranges, and then apples as the four pieces of data we have. And we have one column, which is fruit. So using the relative frequency equation, you can have relative frequency is equal to df. So from the data frame of fruit, we are going to count the values. So value underscore counts will give you the total number of values, but we want to also normalize. If you activate normalize, it will give you relative frequency. If you don't activate it, it will give you just the frequency of each of these types of fruit. So at the very end, you will be able to have, because there's only apples, bananas, and oranges, you should only have 3 values presented, either as a frequency if normalization is false, and as a relative frequency if normalization is true. Now on to percentage and characteristics. Percentage is very closely related to relative frequency. It's just 100 times the relative frequency, and that gives you your percentage. So based on these 3 metrics, there are some key points. As soon as you calculate the relative frequency or the percentage, you can check to see if your calculations are correct. All of your frequencies will have, number one, all of your frequencies will have to equal the total number of measurements you've taken. When you move on to relative frequencies, because you're normalizing all of the data, or if you're using percentage, it's also normalized. It means your relative frequencies must add up to 1, and your percentages must add up to 100% of the entire sample set that you have. When you're choosing categories to use for data analysis, just make sure you have a category for outliers, just in case you have data that doesn't fall within one of your categories, unless it's yes or no, in which case it's very black and white. Next, you also want to ensure that your categories are created in such a way that one measurement must fall into one of your chosen categories, and one measurement must fall into only one category, so that you can streamline your data analysis. Now moving on to plots for categorical data, we're going to go through pie charts, bar charts, some extensions, and then an object-oriented approach to creating figures. So pie charts, they're fun to look at. They're very useful for visualizing frequency distributions of categories. So on the right, I have a breakdown of our class. We have 32 students in the physics and astronomy program, 36 in physics, 4 in science, and 2 in other. So in terms of pie charts, we can use Python code from matplotlib. The majority of our graphs will be coming from matplotlib, unless there's a shorter way of doing it, let's say through pandas or scipy. So first we have, when we're trying to start coding, we have to import the plotting function from, or the plotting package from matplotlib. So it's import matplotlib.pyplot as PLT. The PLT is a way to provide a shortcut so that we don't have to type all of this out every single time when we call a specific function. In most cases, you will also need NumPy. So we can import NumPy as NP. That will help with the calculation and data analysis process. So usually these two are imported as the first steps. And of course, you can go back and import more as required. Now, this information is given to us as a statistical table. We're going to have to create this information and import it as a list. There's 2 ways of importing this information. You can either have this statistical table in a text file or a CSV file and load it into your Python program, or you can, in this case, there's only 4 measurements, so we can simply create 2 lists. One list for programs where we have the names of the programs, and another list of students, which gives you the corresponding frequency of students for each of these programs in the same order. Once you have these 2 lists, you can use the plot.py function. So it's plt.pie. You are going to basically plot your students and have labels of programs. So if you do plt.show, it's going to show your graph and you get something like this. Now, if you go through the chapter notes, there will be additional modifications you can do to what we call explode a piece of the pie out. So let's say we just want to do a more detailed analysis in the physics and astronomy program. You can actually split the 43.2% out and have it kind of elevated from the pie chart so that the reader knows that you're going to focus in on that particular piece of the pie moving forward. Other considerations when we're using pie charts, sometimes it's a good idea, sometimes it's a bad idea. So I have a different example here, primarily because I am able to read all of the programs around this pie chart. There aren't too many slices, and also the percentages are legible. If you have too many categories and if you have overlapping text, it's either time to use a legend or it's time to use a bar graph or something else. Even with a bar graph, if you have too many categories, that usually tells me it's better off using a statistical table to present the data, because having a visualization of so many categories is not very useful. So keep that in mind, make a decision and make a good decision as to how you want to present your data without it being too cluttered. So now we're going to move on to bar charts. Bar charts are usually more common just because they're used to display both categorical and quantitative data. For categorical data, your x-axis pretty much has no choice. It's going to be whatever categories you have. But if you have quantitative data, you can also create categories. For example, if we are talking about temperatures, you can have different range of temperatures from 0 to 5, 5 to 10, things like that, and then create a histogram, which is basically like a bar chart. And then from that histogram, we can create a relative frequency histogram. Those are things that we can go through in the next chapter. So in terms of the Python code, from pie charts to bar charts, everything remains the same, except for over here, you have plt.bar instead of pi, and the syntax does change inside. You now have your x-axis first, which is programs, because I want that at the bottom, and then I have students, which gives me the frequency of students as the height of the bar graph. Some considerations when you are using bar graphs, however, is that you should always label the axes, because right here, all I see is the different programs on the x-axis. If your categories aren't very clear and easy to understand, you will need to have an axis title underneath. On the left side, I really should be labeling it as the number of students, just so it's clear what I'm trying to calculate. Sometimes if you have very, very large values or very large frequencies, you can present values like this, but then have multiplied by 1000 if you don't want to have too many zeros on the left side of your tick marks. Finally, with all of this, you should have a title and also be able to present the exact quantity of each of these students or the frequency. So that statistical table is still important to have alongside your bar graph, or you can plot the value of these frequencies directly within each bar of the bar chart. Okay, so next. Next, I just want to go through some extensions for bar charts because you can do fairly neat things with them. A bar chart doesn't always have to be vertical. So sometimes if you want to present a horizontal bar chart, then just change the code from plt.bar to bar h. So just add the h there and you'll be able to convert it to a horizontal bar chart. Next, sometimes you want to have a more cooler way of presenting your data. If you want to do 3D visualization techniques, then you can definitely do so. Here's one example of the same data set, but in a 3D setting. So the code from matplotlib would be as follows. You can go through the chapter notes for some additional styling techniques, but you'll notice that the way we've coded this is slightly different. And there's a reason for it, because normally with Python, it's a very functional type of approach when we're just applying a function like plot.show or plot.bar. What Python is doing is it's automatically creating the figure for us because we're exporting an image. We have the figure, and then we have the axis automatically created for us, and then we're simply just plotting our data points onto what's already automatically created for us through that function. Sometimes we want a more what we call object-oriented approach. So in this case, when we're trying to do a 3D projection image, we do need that object-oriented approach where we're creating a figure, we're adding a 3D axis to that figure. So before doing any of this, as soon as I have figure and axis and I do plot.show, I would actually see the axis with no data points on it. Then I have my data points here. And afterwards, what I'm going to do is add a bar chart to my axis. So the only axis I have is just y equals 0. So assuming this is x and this is y going into the page, we have x, y, and z. So the y over here, I'm just going to say y equals 0 for my one set of data values. And then I can plot it along this x-axis, whereas my vertical axis would be the z-axis. In terms of being able to plot multiple data sets, I will not be going through that in this lecture. Later on, if we have multiple data sets, you can actually stack them beside each other so you get a wide range of different histograms. It looks very fancy, but it's very hard to compare just because of the depth of all of those bar charts, but you will need to use NumPy arrays to load your data sets, and you will also need to loop through to create multiple plots on your axis at different y values. So these are things that you can either learn yourself later on, or I will be showing you if it's relevant for a specific example that we go through. So just to summarize the object-oriented approach to creating figures, we can approach coding in one of two ways. You can do functional or you can do object-oriented. With functional, it's usually I call a function, it does what it does automatically, and that's basically it. It's a very quick approach to accomplishing what we want. When we do object-oriented approaches, we are calling different elements objects, and we are stacking them on top of each other with some sort of logical sequence. So here, when we have object-oriented creation of figures, we have step-by-step plotting from generating the figure or the canvas to plotting your axes and then plotting your function or your data points. So which way is better for physicists? In terms of plotting, I would say object-oriented plotting is much better as a scientist because we follow certain steps that are very easily understood, just like we would do if we were drawing the graph by hand. So first, you would have to generate the plot. So all of this code is to generate the plot. You would generate the figure by doing plt.figure. It creates a region where you're going to plot your figure, and you can define how big that region is. So if you want to publish a paper or write or present a figure in an essay, then plt.figure allows you to define the size of your figure so it's consistent throughout. Next, once you have your figure or your canvas, you can plot an axis, well, not plot, but you can add an axis to your figure. And so over here, you have a normal axis that's added to your figure. I'll explain 111 in the chapter notes. Once you have your axis, you can plot your data points on that axis. So ax.plot, and you have your x and y points. And then you can show your plot at the end, which will show up in the figure itself. Now, if you want a faster approach to this, instead of having so many steps, you can combine the first two steps together. You have figure, comma, ax for creation of the figure and axes at the same time. So you would set them equal to plt.subplots, which basically creates an axis within the figure, and you can define the figure size based on an aspect ratio. Once you have that, you can simply use your ax or whatever you call your axis. For example, if we had programs for the x-axis, then I would call ax programs, and then you would just plot your points onto your program axis. And of course, at the end, you still have to have the plt.show to show your plot. Finally, onto a summary. Some key concepts and terminology. We definitely want you to understand how to describe qualitative or categorical data through a statistical table. When presenting categorical data, make sure you choose the correct number of categories, and make sure that all of your data can be filtered through and placed into one category only. The other thing to note is that you can use pie charts or bar charts. You should know the Python code for creating both types of charts, whether it's functional or object-oriented. Doesn't matter as much, but you should be able to generate both types of charts for this class.